Welcome to Tech with Koushik. This is set 4 of our AI-300 Microsoft Certified Machine Learning Operations Engineer Associate Practice Question Series. Choose your answer before the timer ends. Then review the correct answer, detailed explanation, and exam tip. Keep track of your score and see how exam ready you are. Each practice set is completely standalone, so you can start here without watching any of the other sets first. Playlist link is in the description. Let us begin set 4. The next item is question number 124. This question focuses on AML registries. A shared Azure machine learning registry contains a version training component and its environment. A production workspace references those registry assets when submitting a pipeline job. The production workspace has its own compute cluster and its own production data asset. For each statement, select yes if the statement is true. Otherwise, select no. The first statement is, the pipeline can reference the component and environment from the registry while executing on compute that belongs to the production workspace. The second statement is, using a registry component requires the production workspace compute cluster itself to be copied into the registry. The third statement is, the production workspace can bind its local data asset to an input of a component retrieved from the registry. The fourth statement is, a component created only in one workspace automatically becomes available to every workspace without being registered or shared through a registry. Statement 1. The answer is yes. Registry components and environments can be consumed by jobs submitted in supported workspaces. Statement 2. The answer is no. Compute is a workspace resource and is not a registry asset. Statement 3. The answer is yes. Registry components can execute with workspace local inputs and compute. Statement 4. The answer is no. Cross-workspace reuse requires an appropriate registry/shared asset. Registry assets are portable. Execution context such as compute and local input stays with the target workspace. Now consider question number 125. Background. A financial organization runs Azure machine learning training jobs that process confidential data. Current environment. The workspace uses a managed virtual network in allow-only approved outbound mode. Its default storage account, key vault, and container registry have public network access disabled. A new private Azure SQL database must also be queried from training jobs. Business requirements. Managed compute must have no unrestricted internet egress, and all listed Azure dependencies must be reached privately. Technical requirements. Use Azure Machine Learning Managed Network capabilities rather than opening the Azure SQL database publicly. Which 3 configurations are appropriate? Choose 3. Choose every option that satisfies the requirement. The options are: Choice A. Keep the workspace Managed Network Isolation mode set to allow only approved outbound. Choice B. Configure a managed private endpoint outbound rule from the workspace network to the Azure SQL database. Choice C. Ensure private connectivity exists for the workspace dependency resources such as storage, key vault, and container registry. Choice D. Enable a public SQL endpoint and restrict it only with a database password. Choice E. Add a broad internet FQDN rule that allows all outbound destinations. The required selections are option A. Keep the workspace Managed Network Isolation mode set to allow only approved outbound. Option B. Configure a managed private endpoint outbound rule from the workspace network to the Azure SQL database. And option C. Ensure private connectivity exists for the workspace dependency resources such as storage, key vault, and container registry. Here is the technical justification. Allow only approved outbound restricts managed compute egress. Private endpoint rules provide approved private paths to additional dependencies, while private connectivity to core workspace resources keeps their public access disabled. D. A public endpoint contradicts the private access requirement. E. Broad internet egress defeats the intended data exfiltration control. Remember this distinction for the exam. AML Managed Network Isolation controls compute egress. Add explicit approved outbound/private endpoint rules for required private dependencies. Proceed to question number 126. This one is marked hard. Eliminate the options systematically. Consider this scenario. A company deploys Azure machine learning infrastructure from GitHub. Pull requests may validate bicep, but production deployment must use GitHub OIDC, require an environment approval, and avoid stored Azure client secrets. Select the 5 required actions and arrange them in a logical implementation order. One item will not be used. The available items are The first available item is configure the GitHub workflow to request an OIDC token and sign in with Azure login. The second available item is create the Microsoft intra-application or user-assigned managed identity used by the workflow. The third available item is configure a federated identity credential that trusts the intended GitHub repository, branch, or environment. The fourth available item is assign the Azure identity the least privilege or BAC permissions required at the deployment scope. The fifth available item is place the production deployment job behind a protected GitHub environment approval and run the bicep deployment after approval. The sixth available item is store a client secret in the repository and use it instead of federation. Arrange the items in this order. The first item is create the Microsoft intra-application or user-assigned managed identity used by the workflow. The second item is configure a federated identity credential that trusts the intended GitHub repository, branch, or environment. The third item is assign the Azure identity the least privilege or BAC permissions required at the deployment scope. The fourth item is configure the GitHub workflow to request an OIDC token and sign in with Azure login. The fifth item is place the production deployment job behind a protected GitHub environment approval and run the bicep deployment after approval. OIDC requires an Azure identity and a federated trust relationship before GitHub can obtain Azure credentials. The identity must be authorized at the target scope, and the deployment job can then use token-based login behind an environment approval. A useful examination rule is this. GitHub to Azure OIDC combines federated trust, Azure RBAC, token-enabled login, and optional protected environment promotion gates. Let us examine question number 127. Let us first review the situation. An Azure machine learning pipeline in production references a command component version and a registered environment version. Security requires a patched runtime image, but historical pipeline runs must remain reproducible. Complete the lifecycle strategy. Statement 1. Register the patched runtime as the blank. Choose between 1. A new environment version, an in-place replacement of the existing environment version, or a job tag only. Statement 2. Register the component that references the patched runtime as the blank if the component definition changes. Choose between 2. A new component version, the existing component version modified in place, or an unregistered local script. Statement 3. Keep production pipelines pinned to the blank until the patch combination has passed validation. Choose between 3. Explicit tested asset versions, the latest label without validation, or whichever environment image was built most recently. For Statement 1, select a new environment version. Updating runtime dependencies should create a new reproducible environment asset version. For Statement 2, select a new component version. A changed component definition should be versioned instead of silently mutating the existing definition. For Statement 3, select explicit tested asset versions. Explicit versions prevent unvalidated latest assets from changing production behavior. The key takeaway is treat environments and components as version dependencies. Production reproducibility requires explicit validated versions. Question number 128. The focus now shifts to automated ML. Background. A credit risk team uses Azure Machine Learning AutoML classification to explore candidate models. Current environment. The team needs repeatable comparisons, a business-approved primary metric, and promotion only when the best candidate exceeds a minimum validation threshold. Business requirements. The experiment must remain traceable in Azure Machine Learning, and the selected model must be governed as a registered model asset before deployment. Technical requirements. Use AutoML and MLflow-compatible experiment tracking rather than manually editing algorithms between runs. Which 3 actions best satisfy the requirements? Choose 3. Identify all valid responses. Option A. Configure an AutoML classification job with the agreed primary metric. Option B. Compare the completed AutoML trials by using tracked metrics and identify the best qualifying candidate. Option C. Register the selected qualifying model as a version model asset before production deployment. Option D. Deploy the first completed trial before comparing its metrics. Option E. Replace AutoML with a batch endpoint because batch endpoints perform model search. Select Option A. Configure an AutoML classification job with the agreed primary metric. Option B. Compare the completed AutoML trials by using tracked metrics and identify the best qualifying candidate. And option C, register the selected qualifying model as a version model asset before production deployment. The key reason is AutoML explores candidate models against a configured objective. The team should compare tracked trial metrics, enforce the business threshold, and register the approved model to establish a governed version before deployment. The incorrect choices fail for the following reasons. D. First completion does not imply best or acceptable performance. E. Batch endpoints perform inference, not AutoML model search. Keep this examination point in mind. AutoML search, metric-based candidate selection, and model registration are separate lifecycle stages. Question number 129. Review the situation. An Azure machine learning sweep job maximizes validation accuracy. Trials that are clearly uncompetitive should stop early. The team wants a policy that compares each trial with the best performing trial and stops runs that fall outside an allowed relative margin. Complete the sweep configuration. The first statement reads, use the blank early termination policy. The options for this statement are 1. Bandit, median stopping, or truncation selection. The second statement reads, express the relative tolerance from the best run with the blank. The options for this statement are 2. Slack _ factor, truncation _ percentage, or max _ concurrent _ trials. The third statement reads, configure the blank to control how frequently the policy is evaluated. The options for this statement are 3. Evaluation _ interval, sampling _ algorithm, or objective _ name. The correct value for statement 1 is bandit. Bandit terminates trials that fall sufficiently behind the current best run. The correct value for statement 2 is slack _ factor. Slack _ factor represents the permitted relative performance difference. The correct value for statement 3 is evaluation _ interval. The interval controls when the early termination check occurs. Exam tip. Bandit equals best run comparison. Median stopping equals population median. Truncation equals periodically drop a fraction of low performers. The next item is question number 130. This is a harder question, so check every requirement carefully. Background. A PyTorch language model training script uses distributed data parallel and Azure Machine Learning SDKv2. Current environment. The job must use 3 GPU nodes with 4 GPUs per node. The same hyperparameters must be used by all workers in this single distributed training run. Business requirements. Use one distributed training job rather than separate independent trials. Technical requirements. Launch one worker process per GPU and allocate all 3 nodes. Which 3 configuration choices are appropriate? Choose 3. Select all answers that apply. Review the options. Choice A. Set instance _ count to 3. Choice B. Configure PyTorch distribution with process _ count _ per _ instance set to 4. Choice C. Keep the workload as one command job with distributed execution. Choice D. Convert the job to a sweep job with 12 independent child trials. Choice E. Set instance _ count to 12 and process _ count _ per _ instance to 1 so each GPU becomes a separate node. The correct answers are option A. Set instance _ count to 3. Option B. Configure PyTorch distribution with process _ count _ per _ instance set to 4, and option C. Keep the workload as one command job with distributed execution. The requirement is satisfied because instance _ count allocates 3 nodes. Process _ count _ per _ instance launches 4 workers per node, typically 1 per GPU. A distributed command job coordinates those workers as one training run using the same hyperparameters. The other choices do not satisfy the requirement because D. A sweep creates independent hyperparameter trials rather than one distributed run. E. Instance _ count represents nodes, not individual GPUs. Distributed training scales one trial across workers. Sweep jobs scale independent trials across hyperparameter configurations. Proceed to question number 131. Scenario. A training pipeline produces an MLflow model in a development workspace. The model must be evaluated, registered in that workspace, promoted to a central registry, and then deployed from the registry into the production workspace. Arrange the 5 actions in the most defensible promotion order. The sequence must use these items. Entry 1. Share the approved registered model version from the development workspace to the central registry. Entry 2. Deploy the registry model version to the production workspace endpoint. Entry 3. Register the MLflow model from the successful training job output in the development workspace. Entry 4. Evaluate the produced model and confirm it meets the promotion criteria. Entry 5. Run the training pipeline and produce the MLflow model output. Here is the proper order. In position 1, run the training pipeline and produce the MLflow model output. In position 2, evaluate the produced model and confirm it meets the promotion criteria. In position 3, register the MLflow model from the successful training job output in the development workspace. In position 4, share the approved registered model version from the development workspace to the central registry. In position 5, deploy the registry model version to the production workspace endpoint. The reasoning is as follows. The model must exist before evaluation, and only an approved artifact should be registered and promoted. The registry then becomes the governed cross-workspace source used for production deployment. Remember this distinction for the exam. Separate model creation, evaluation, workspace registration, registry promotion, and production deployment. Now consider question number 132. We are moving to progressive rollout. Scenario. A managed online endpoint has a stable blue deployment. A new green deployment must receive production-shaped requests for observation, but user responses must continue to come only from blue during the initial validation phase. For each statement, select yes if the statement is true. Otherwise, select no. Statement 1. Mirroring a percentage of endpoint traffic to green can send copies of requests to green while clients still receive the blue response. Statement 2. Assigning green 10% of normal endpoint traffic is equivalent to shadow mirroring because clients never receive green responses. Statement 3. Requests sent directly to a named deployment are not the traffic source used for endpoint-level shadow mirroring. Statement 4. After successful shadow validation, traffic allocation can be changed to send a controlled percentage of live responses from green. The answer to statement 1 is yes. Shadow traffic validates the candidate without returning candidate responses. The answer to statement 2 is no. Normal traffic allocation returns green responses for the requests routed to green. The answer to statement 3 is yes. Mirroring applies to traffic routed through the endpoint without explicitly targeting a deployment. The answer to statement 4 is yes. Traffic splitting supports progressive exposure after validation. A useful examination rule is this. Mirror traffic for shadow testing. Use traffic allocation when clients should begin receiving responses from the candidate deployment. The next item is question number 133. Background. A managed online deployment succeeds during creation, but returns intermittent HTTP 5xx responses under production load. Current environment. The scoring script works for small tests. CPU utilization approaches saturation, request latency increases sharply, and container logs show no model loading failure. Business requirements. Identify whether the incident is primarily a serving capacity problem before changing the model. Technical requirements. Use endpoint observability and scaling controls. Which 3 actions should the operations team perform first? Choose 3. More than one answer may be correct. Available choices. Option A. Correlate request latency, request rate, CPU/resource utilization, and deployment logs during the incident window. Option B. Review or increase autoscaling capacity if utilization and concurrency indicate insufficient serving resources. Option C. Reproduce representative load against the endpoint after the scaling change and compare failure and latency metrics. Option D. Retrain the model with a larger training dataset before checking infrastructure metrics. Option E. Archive the registered model because archiving automatically scales the deployment. The choices that satisfy the requirement are Option A. Correlate request latency, request rate, CPU/resource utilization, and deployment logs during the incident window. Option B. Review or increase autoscaling capacity if utilization and concurrency indicate insufficient serving resources. And Option C. Reproduce representative load against the endpoint after the scaling change and compare failure and latency metrics. This is correct because the symptoms point to load-related serving pressure. Correlating telemetry identifies the bottleneck, scaling addresses capacity if confirmed, and repeatable load testing validates whether the change resolves the failure and latency pattern. The alternatives can be eliminated because D. Retraining does not address demonstrated resource saturation. E. Model archiving does not scale an active deployment. The key takeaway is troubleshoot endpoint incidents by correlating load, latency, resource saturation, logs, and scaling before changing model training. Now consider question number 134. Take extra care here because this is a hard question. Background. A binary classifier is deployed to production. True outcomes become available 7 days after each prediction. Current environment. Input distributions are stable, but business users suspect predictive quality is degrading. Business requirements. Measure actual production accuracy rather than inferring performance only from feature drift. Technical requirements. Use Azure Machine Learning Model Monitoring and delayed ground truth data. Which 3 actions are appropriate? Choose 3. Choose every option that satisfies the requirement. The options are: Choice A, collect or register production predictions together with the delayed ground truth outcomes in a form usable by model monitoring. Choice B, configure a model performance monitoring signal that compares predictions with ground truth. Choice C, set thresholds on relevant model performance metrics and alert when they are breached. Choice D, use only data drift metrics because ground truth is unavailable at prediction time. Choice E, replace the model performance signal with endpoint CPU utilization. The required selections are option A, collect or register production predictions together with the delayed ground truth outcomes in a form usable by model monitoring. Option B, configure a model performance monitoring signal that compares predictions with ground truth. And option C, set thresholds on relevant model performance metrics and alert when they are breached. Here is the technical justification. True production model quality requires comparing predictions with actual outcomes. Azure Machine Learning Model Performance Monitoring can use ground truth when it becomes available and evaluate configured performance metrics against thresholds. Now consider why the remaining options are unsuitable. D. Drift is an indirect signal and cannot replace ground truth performance measurement. E. CPU utilization measures serving infrastructure, not predictive quality. Keep this examination point in mind. Use model performance signals when actual outcomes are available. Drift and infrastructure metrics answer different questions. Question number 135. Review the situation. An Azure Machine Learning Model Monitor fails when a configured quality threshold is breached. The organization wants an event-driven retraining workflow rather than a fixed daily retraining schedule. Select the 4 required actions and arrange them in a logical operational sequence. One item will not be used. Review the items to be ordered. Item 1. Filter the event grid subscription for the relevant Azure Machine Learning Run Status event and monitor threshold breach tag or signal. Item 2. Configure model monitoring with the required signal and threshold. Item 3. Route the filtered event grid event to an automation target that starts the retraining or remediation workflow. Item 4. Validate the retrained candidate and promote it only if acceptance criteria are met. Item 5. Retrain every model continuously regardless of monitoring results. The completed sequences. First, configure model monitoring with the required signal and threshold. Second, filter the event grid subscription for the relevant Azure Machine Learning Run Status event and monitor threshold breach tag or signal. Third, route the filtered event grid event to an automation target that starts the retraining or remediation workflow. Fourth, validate the retrained candidate and promote it only if acceptance criteria are met. Monitoring must produce the threshold event first. Event grid can filter the relevant Azure Machine Learning Run Status change and threshold breach metadata, then invoke automation that retrains or remediates. The new candidate still requires validation. Exam tip. A monitoring breach can trigger retraining, but retraining output should still pass evaluation and promotion gates. Proceed to question number 136. This question moves us into Foundry Managed Identity. Background. A Microsoft Foundry or AG agent queries Azure AI search and reads source documents from Azure Blob Storage. Current environment. Both services use Microsoft Intra authentication. API keys and storage keys are prohibited. Business requirements. The runtime must have only the minimum data plane permissions required to query the search index and read source blobs. Technical requirements. Use the Foundry project's managed identity. Which 3 actions best satisfy the requirements? Choose 3. Select all answers that apply. Review the options. Option A. Enable or use the project's managed identity for runtime authentication. Option B. Assign search index data reader to the project identity on the Azure AI search service. Option C. Assign storage blob data reader to the project identity on the source storage account. Option D. Assign owner to the project identity on the subscription. Option E. Store the search admin key and storage account key in project environment variables. The correct answers are Option A. Enable or use the project's managed identity for runtime authentication. Option B. Assign search index data reader to the project identity on the Azure AI search service. And Option C. Assign storage blob data reader to the project identity on the source storage account. The key reason is managed identity provides credentialless authentication. Search index data reader grants read-only query access to Azure AI search, while storage blob data reader grants read-only blob access to the source documents. The remaining options are incorrect because D. Subscription owner is far beyond the required data plane permissions. E. Stored service keys violate the keyless access requirement. For Foundry are AG, separate authentication from authorization. Managed identity authenticates. Resource data plane roles authorize the required operations. Proceed to question number 137. A company is designing a new network-isolated Microsoft Foundry hosted agent environment. It will use a customer-managed virtual network for outbound isolation and a private endpoint for inbound access. For each statement, select yes if the statement is true. Otherwise, select no. Review Statement 1. A bring-your-own virtual network design uses a dedicated delegated subnet for the agent runtime and gives the organization control over routing and peering. Review Statement 2. A private endpoint by itself isolates both inbound traffic and all agent outbound traffic. Review Statement 3. For hosted agent virtual network injection, the network injection configuration should be included when the Foundry account is initially created rather than added later. Review Statement 4. A managed virtual network is an alternative when full isolation is needed, but Microsoft should manage the network address space and infrastructure. Statement 1 should be marked yes. BYOVNet is designed for customer-controlled network address space and routing. Statement 2 should be marked no. A private endpoint secures inbound access. Outbound isolation requires the selected egress model. Statement 3 should be marked yes. Current hosted agent guidance requires VNet injection to be configured at account creation. Statement 4 should be marked yes. Managed VNet provides isolated egress without requiring customer network management. Remember this distinction for the exam. In Foundry networking, decide egress isolation separately from inbound private access and plan hosted agent network injection at account creation. We will now analyze question number 138. This is a hard-level item, so avoid choosing too quickly. Consider the following scenario. An enterprise must select serving modes for 4 production inference patterns in Microsoft Foundry. Match each requirement to the most appropriate deployment pattern. A deployment pattern may be used more than once. Review the items in the left column. Left item 1. Globally distributed interactive traffic with variable demand and paper token consumption. Left item 2. Sustained high-volume interactive traffic requiring reserved model throughput. Left item 3. Large asynchronous inference jobs where completion can occur later. Left item 4. An open-source model that must run on dedicated Foundry-managed GPU capacity. Choose matches from the following right-side entries. Right option A, global standard. Right option B, global provisioned. Right option C, global batch. Right option D, managed compute. Here are the completed matches. Pair globally distributed interactive traffic with variable demand and paper token consumption. And global standard. Pair sustained high-volume interactive traffic requiring reserved model throughput. And global provisioned. Pair large asynchronous inference jobs where completion can occur later. And global batch. Pair an open-source model that must run on dedicated Foundry-managed GPU capacity. And managed compute. The requirement is satisfied because each deployment pattern addresses a different operational requirement. Consumption-based global serving, reserved PTU capacity, asynchronous batch processing, or dedicated managed GPU hosting. A useful examination rule is this. Choose deployment type from traffic shape, latency expectation, billing/capacity model, and model hosting requirement. Now consider question number 139. Background. A global generative AI application is moving from global standard to global provision capacity. Current environment. The selected model is supported for global provisioned in the target region, but deployment creation fails because capacity cannot be allocated. Business requirements. Maintain the same model family and region if possible. Technical requirements. Diagnose quota and sizing before changing application code. Which 3 checks are most relevant? Choose 3. Identify all valid responses. Available choices. Choice A. Verify the subscription's global provisioned PTU quota in the target region. Choice B. Verify the model's minimum PTU requirement and requested deployment capacity. Choice C. Confirm that actual regional capacity is available for the requested model and deployment type. Choice D. Increase Azure Virtual Machine virtual CPU quota because PTU allocation is controlled by VM quota. Choice E. Increase the application's max_token setting because token limits determine subscription PTU quota. The choices that satisfy the requirement are Option A. Verify the subscription's global provision PTU quota in the target region. Option B. Verify the model's minimum PTU requirement and requested deployment capacity. And Option C. Confirm that actual regional capacity is available for the requested model and deployment type. The reasoning is as follows. Provision deployment depends on quota, model-specific minimum sizing, and available model capacity for the target region/deployment type. All 3 can block allocation even when the model is otherwise supported. D. PTU capacity is not governed by VM virtual CPU quota. E. Application max_tokens does not set subscription PTU quota. The key takeaway is PTU deployment failures require checking model support, minimum PTUs, quota, and actual regional capacity, not VM quota. Review question number 140. Carefully. Next, we enter the topic of managed model compute. Background. A company deploys an open-source model to Microsoft Foundry Managed Compute. Current environment. Application insights shows sustained CPU and memory pressure during representative load, while request duration rises. The model quality is acceptable. Business requirements. Improve serving stability without switching model families. Technical requirements. Keep the model on managed compute and validate any capacity change with production-like load. Which 3 actions are appropriate? Choose 3. More than one answer may be correct. Review each available choice. Option A is review resource usage and request duration telemetry for the deployed workload. Option B is increase the next deployment or version's allocated compute resources when sustained utilization is too high. Option C is retest with representative load after changing the resource allocation. Option D is fine-tune the model immediately because CPU saturation proves model quality degradation. Option E is replace the deployment with a prompt-only evaluator because evaluators provide serving capacity. Select Option A. Review resource usage and request duration telemetry for the deployed workload. Option B. Increase the next deployment or version's allocated compute resources when sustained utilization is too high. And Option C. Retest with representative load after changing the resource allocation. This is correct because the observed pressure is operational capacity, not model quality. Managed compute right-sizing should use telemetry, adjust CPU/memory/GPU resources when sustained utilization is excessive, and then be validated with representative load. The incorrect choices fail for the following reasons. D. Resource saturation does not prove model quality degradation. E. Evaluators measure quality and do not provide serving capacity. Keep this examination point in mind. Right-size managed compute from observed resource use and request performance. Then retest after each immutable deployment/version change. The next item is question number 141. Consider this scenario. A hosted agent in Microsoft Foundry is being updated with a new immutable version that changes its resource allocation and instructions. The team must verify the candidate before directing production traffic to it. Arrange the 5 actions in the safest operational order. Build the sequence from the following entries. The first available item is observe candidate runtime telemetry and evaluation results under representative load. The second available item is create the new agent version with the updated configuration. The third available item is promote or route production use to the validated new version. The fourth available item is run pre-production functional, quality, safety, and performance tests against the candidate version. The fifth available item is keep the previous known good version available until the observation period for the new version is complete. The correct sequence is as follows. In position 1, create the new agent version with the updated configuration. In position 2, run pre-production functional, quality, safety, and performance tests against the candidate version. In position 3, observe candidate runtime telemetry and evaluation results under representative load. In position 4, promote or route production use to the validated new version. In position 5, keep the previous known good version available until the observation period for the new version is complete. Here is the technical justification. Version deployment separates candidate creation from validation and production promotion. Pre-production testing and runtime observation reduce risk, while retaining the prior version provides a rollback target. Exam tip. Treat agent versions like production releases. Create, evaluate, observe, promote, and retain rollback capability. Question number 142. This is a harder question, so check every requirement carefully. Background. A support application stores prompts in Git and deploys through GitHub Actions. Current environment. A pull request changes the system prompt and retrieval instructions. The application code and model deployment remain unchanged. Business requirements. Prompt changes must be reproducible, reviewable, and blocked from production when quality or safety regresses. Technical requirements. Use source control and automated evaluation. Which 3 controls should the team implement? Choose 3. Select all answers that apply. Option A. Version prompt definitions in Git so the exact production prompt can be traced to a commit. Option B. Run a repeatable evaluation suite against the changed prompt during CI. Option C. Fail the promotion workflow when configured quality or safety thresholds are not met. Option D. Store the latest prompt only in a developer's local environment to reduce repository changes. Option E. Promote every prompt change automatically because model weights are unchanged. The choices that satisfy the requirement are Option A. Version prompt definitions in Git so the exact production prompt can be traced to a commit. Option B. Run a repeatable evaluation suite against the changed prompt during CI. And Option C. Fail the promotion workflow when configured quality or safety thresholds are not met. Git provides reproducible prompt history, while CI evaluation measures the behavioral effect of the change. Threshold-based gating prevents a prompt-only change from bypassing production quality and safety controls. The other choices do not satisfy the requirement because D. Local-only prompt state is not reviewable or reproducible. E. Prompt changes can materially alter behavior even when model weights are unchanged. Prompts are production artifacts. Version them, evaluate changes, and gate promotion just like application code or model versions. Let us work through question number 143. Begin by examining the scenario. A Microsoft Foundry team needs domain-specific evaluation logic that is not fully covered by built-in evaluators. Match each requirement to the most appropriate custom evaluator type. Each evaluator type is used once. The left side items are: Item 1 on the left. Deterministically fail responses that violate a JSON schema and compute a rule-based score without network access. Item 2 on the left. Judge subjective brand tone by asking a model to return an ordinal score and reason. Item 3 on the left. Score outputs by calling an existing proprietary evaluation service that requires network access to an external HTTP endpoint. Now review the right side options. Choice A on the right, code-based custom evaluator. Choice B on the right, prompt-based custom evaluator. Choice C on the right, endpoint-based custom evaluator. The correct matches are as follows. Match deterministically fail responses that violate a JSON schema and compute a rule-based score without network access. With code-based custom evaluator. Match judge subjective brand tone by asking a model to return an ordinal score and reason. With prompt-based custom evaluator. Match score outputs by calling an existing proprietary evaluation service that requires network access to an external HTTP endpoint. With endpoint-based custom evaluator. The key reason is code-based evaluators implement deterministic Python scoring in a sandbox. Prompt-based evaluators use a judge model for subjective criteria. Endpoint-based evaluators call an external HTTP service when proprietary logic or network access is required. Remember this distinction for the exam. Choose custom evaluator type from scoring logic, deterministic code, LLM judgment, or external network scoring service. Now consider question number 144. Background. A multi-turn customer service agent is being evaluated before release. Current environment. The team needs to assess whether the overall conversation completes the user's task, whether responses remain coherent across turns, and whether individual outputs contain hate or unfairness risks. Business requirements. Use Foundry evaluators at the scope where each metric is supported. Technical requirements. Do not replace safety evaluation with a general quality score. Which 3 evaluation choices best satisfy the requirements? Choose 3. Identify all valid responses. The options are: Choice A. Use a conversation-level task completion evaluator for the full interaction. Choice B. Use a conversation-level coherence evaluator for the full interaction. Choice C. Use a turn-level hate/unfairness safety evaluator for individual generated outputs. Choice D. Use only fluency for the entire conversation because fluency subsumes task completion and safety. Choice E. Use endpoint latency as the safety evaluator. The required selections are Option A. Use a conversation-level task completion evaluator for the full interaction. Option B. Use a conversation-level coherence evaluator for the full interaction. And Option C. Use a turn-level hate/unfairness safety evaluator for individual generated outputs. The requirement is satisfied because task completion and coherence can evaluate the conversation as a whole, while harmful content safety evaluators are applied to individual turns. Each metric must be used at a supported scope that matches the required risk or quality property. The alternatives can be eliminated because D. Fluency does not measure task completion or harmful content. E. Latency is an operational metric, not a safety evaluator. A useful examination rule is this: evaluation scope matters. Conversation metrics assess end-to-end interactions, while safety checks commonly evaluate individual generated turns. We will now analyze question number 145. Review the scenario carefully. A new Foundry agent has no production traffic yet. The team wants a reusable evaluation dataset before launch by generating representative synthetic test queries, running them against the candidate agent, and storing the generated cases for later regression tests. Select the 4 required actions and arrange them in a logical sequence. One item will not be used. The available items are: Entry 1. Define the synthetic data generation prompt and optional seed/reference material. Entry 2. Generate representative test queries and run them against the target agent or model. Entry 3. Evaluate the generated responses with the selected evaluators. Entry 4. Save or reuse the generated queries as a version project dataset for later evaluations. Entry 5. Wait for several months of production traffic before creating any evaluation data. Here is the proper order. The first item is define the synthetic data generation prompt and optional seed/reference material. The second item is generate representative test queries and run them against the target agent or model. The third item is evaluate the generated responses with the selected evaluators. The fourth item is save or reuse the generated queries as a version project dataset for later evaluations. The reasoning is as follows. Synthetic evaluation begins with a generation prompt and optional seed material. The generated queries are run against the target and scored by evaluators. The resulting queries can then be stored and reused for regression testing. The key takeaway is synthetic evaluation is valuable before production traffic exists. Generate, execute, score, and preserve reusable test cases. Question number 146. Background. A Foundry agent's monthly cost and P95 latency rise after a release. Current environment. Request volume is stable. Traces show that the new version performs additional tool calls and passes substantially more retrieved context to the model. Business requirements. Determine whether the regression is caused by larger prompts, larger responses, or additional execution steps. Technical requirements. Use trace and usage telemetry rather than guessing from model list price alone. Which 3 observations should the team correlate first? Choose 3. Choose every option that satisfies the requirement. Available choices. Option A. Input token consumption per request. Option B. Output token consumption per request. Option C. Trace spans for model/tool calls together with latency for those spans. Option D. Number of Git branches in the repository. Option E. Number of Azure resource groups in the subscription. The correct answers are option A, input token consumption per request, option B, output token consumption per request, and option C, trace spans for model/tool calls together with latency for those spans. This is correct because input and output token telemetry reveal model consumption growth, while traces show additional calls and where latency accumulates. Together, they distinguish larger prompts, larger completions, and extra execution steps. Now consider why the remaining options are unsuitable. D. Repository branches do not explain runtime cost. E. Resource group count is unrelated to per-request GenAI execution. Keep this examination point in mind. Use tokens plus traces to explain GenAI cost/latency regressions. One metric alone may hide extra calls or expanded context. Question number 147 requires careful analysis. Pay close attention to every stated constraint. A team is choosing among supervised fine-tuning, SFT, direct preference optimization, DPO, and reinforcement fine-tuning, RFT. Select the best customization method for each data and optimization pattern. Choose the correct entry for every drop-down field. Review Statement 1. The team has high-quality input-output examples with clearly desired target responses for a domain task, the blank. The available choices are 1. SFT, DPO, or RFT. Review Statement 2. The team has pairs of preferred and non-preferred responses for subjective style and alignment, the blank. The available choices are 2. SFT, DPO, or RFT. Review Statement 3. The task has objectively gradable outcomes and requires optimization from reward signals rather than only target response pairs, the blank. The available choices are 3. SFT, DPO, or RFT. The answer to the first statement is SFT. Supervised fine-tuning is the standard starting point for learning from explicit target demonstrations. The answer to the second statement is DPO. Direct preference optimization uses paired preference data for alignment. The answer to the third statement is RFT. Reinforcement fine-tuning uses grader/reward signals to optimize complex objectively measurable behaviors. Exam tip. SFT equals demonstrations. DPO equals preference pairs. RFT equals reward-driven optimization for objectively gradable behavior. Proceed to question number 148. The focus now shifts to synthetic fine-tuned data. Background. A regulated organization wants to create synthetic fine-tuning data in Microsoft Foundry because real customer conversations cannot be used. Current environment. The team has a clean domain policy document and plans to generate question-answer examples for supervised fine-tuning. Business requirements. The generated dataset must remain representative and must be validated before expensive training. Technical requirements. Use Foundry synthetic data generation and preserve a held-out evaluation path. Which 3 practices are appropriate? Choose 3. More than one answer may be correct. Review the options. Option A. Use the domain document as the reference material for synthetic Q&A generation. Option B. Review generated samples and adjust the reference material or generation settings before scaling to a large dataset. Option C. Keep validation or evaluation data separate so the fine-tuned model can be checked for generalization and regression. Option D. Treat every generated sample as ground truth without review because synthetic generation guarantees correctness. Option E. Remove all evaluation because training loss alone proves production quality. Select Option A. Use the domain document as the reference material for synthetic Q&A generation. Option B. Review generated samples and adjust the reference material or generation settings before scaling to a large dataset. And Option C. Keep validation or evaluation data separate so the fine-tuned model can be checked for generalization and regression. Here is the technical justification. Synthetic data generation can derive task examples from clean reference material, but generated outputs still require quality review. A separate validation/evaluation path is necessary to detect overfitting and regressions after fine-tuning. The remaining options are incorrect because D. Synthetic data is not guaranteed correct. E. Training loss alone does not prove production quality, safety, or generalization. Synthetic data expands training coverage, but still requires human/data quality review and independent validation. Next, question number 149. Background. ARAG application uses hybrid retrieval. The team is considering a candidate configuration that changes chunking, top K, and semantic re-ranking. Current environment. The baseline is already in production. Business requirements. Promote only a configuration that improves retrieval quality without reducing answer groundedness. Technical requirements. Use the same representative evaluation set for baseline and candidate. Which 3 practices are required for a defensible comparison? Choose 3. Select all answers that apply. Choices. Option A. Run both baseline and candidate against the same representative queries and source corpus. Option B. Compare retrieval relevance metrics and answer groundedness using the same evaluator definitions. Option C. Predefine acceptance and regression thresholds before promotion. Option D. Change the evaluation dataset for the candidate so it better matches the candidate's retrieved results. E. Promote the candidate when it returns more chunks, regardless of relevance. The choices that satisfy the requirement are Option A. Run both baseline and candidate against the same representative queries and source corpus. Option B. Compare retrieval relevance metrics and answer groundedness using the same evaluator definitions. And Option C. Predefine acceptance and regression thresholds before promotion. A controlled RAG comparison holds evaluation inputs and metrics constant, measures both retrieval and answer quality, and uses predefined gates to avoid subjective promotion decisions. D. Changing the candidate dataset invalidates direct comparison. E. More retrieved chunks do not imply better relevance or grounding. Remember this distinction for the exam. For our RAG experiments, control the dataset and metrics, then promote only against predefined relevance and groundedness criteria. The next item is question number 150. A supervised fine-tuning job produces a candidate model. The organization requires a low-cost validation deployment, production promotion only after quality and safety checks, post-release monitoring, and a rollback path. Arrange the 6 actions in the safest lifecycle order. The sequence must use these items. Item 1. Deploy the validated fine-tuned model using the production deployment type that meets availability and residency requirements. Item 2. Run the fine-tuning job and review training results and checkpoints. Item 3. Create a temporary low-cost candidate deployment appropriate for evaluation. Item 4. Evaluate the candidate against representative quality, safety, latency, and cost criteria. Item 5. Monitor the production fine-tuned model and compare it with the approved baseline or thresholds. Item 6. Retain or restore a known good deployment if production evaluation or monitoring reveals an unacceptable regression. The completed sequence is: first, run the fine-tuning job and review training results and checkpoints. Second, create a temporary low-cost candidate deployment appropriate for evaluation. Third, evaluate the candidate against representative quality, safety, latency, and cost criteria. Fourth, deploy the validated fine-tuned model using the production deployment type that meets availability and residency requirements. Fifth, monitor the production fine-tuned model and compare it with the approved baseline or thresholds. Sixth, retain or restore a known good deployment if production evaluation or monitoring reveals an unacceptable regression. The key reason is a fine-tuned model should be inspected before deployment, evaluated in a low-risk candidate environment, promoted only after passing gates, and continuously monitored after release. A known good deployment provides recovery if a regression appears. A useful examination rule is this: fine-tuned model operations span training, candidate testing, gated promotion, production monitoring, and rollback, not training alone. Question number 151. Next, we enter the topic of AML endpoint selection. Review the situation. A platform team must operationalize for inference workloads in Azure Machine Learning. Match each workload to the most appropriate inference option. Each option may be used more than once. The first set contains: left side entry 1. A fraud API must return a prediction synchronously within a few hundred milliseconds for each transaction. Left side entry 2. A nightly job must score millions of files stored in Azure storage and can complete asynchronously. Left side entry 3. A long-running ML pipeline must be exposed for on-demand asynchronous execution over large datasets. Left side entry 4. A custom model requires real-time HTTP scoring and traffic splitting between 2 deployments. The right side choices are: right side entry A, managed online endpoint. Right side entry B, batch endpoint. Use the following matching result. Left item 1. A fraud API must return a prediction synchronously within a few hundred milliseconds for each transaction. Pairs with managed online endpoint. Left item 2. A nightly job must score millions of files stored in Azure storage and can complete asynchronously. Pairs with batch endpoint. Left item 3. A long-running ML pipeline must be exposed for on-demand asynchronous execution over large datasets. Pairs with batch endpoint. Left item 4. A custom model requires real-time HTTP scoring and traffic splitting between two deployments. Pairs with managed online endpoint. The requirement is satisfied because managed online endpoints are designed for synchronous low-latency HTTP inference and support traffic splitting. Batch endpoints create asynchronous jobs and are appropriate for long-running inference over large data or operationalized pipeline components. The key takeaway is online equals synchronous low-latency serving. Batch equals asynchronous job-based inference or pipeline execution over large data. Question number 152. Now, a machine learning team needs different Azure machine learning compute patterns for exploration and repeatable training. Match each requirement to the most appropriate managed compute option. Each option is used once. Begin with the following left side entries. Item 1 on the left. A data scientist needs an interactive development machine with notebooks, terminal access, and persistent user workspace. Item 2 on the left. A production training pipeline needs reusable auto-scaling compute that can scale from 0 to multiple nodes. Item 3 on the left. A team wants Azure Machine Learning to choose and manage job compute without pre-creating a compute target. The second set contains Choice A on the right, compute instance. Choice B on the right, compute cluster. Choice C on the right, serverless compute. The correct pairings are: the correct match for a data scientist needs an interactive development machine with notebooks, terminal access, and persistent user workspace is compute instance. The correct match for a production training pipeline needs reusable auto-scaling compute that can scale from 0 to multiple nodes is compute cluster. The correct match for a team wants Azure Machine Learning to choose and manage job compute without pre-creating a compute target is serverless compute. The reasoning is as follows. A compute instance is a managed interactive development machine. A compute cluster is a reusable auto-scaling target for jobs. Serverless compute lets Azure Machine Learning provision and manage job compute without requiring the team to create a compute target first. Keep this examination point in mind. Compute instance equals interactive development. Cluster equals reusable scalable job compute. Serverless equals Azure Managed Job Compute Lifecycle. Now consider question number 153. We are moving to AML environment builds. Background. A regulated Azure Machine Learning workspace uses a private Azure container registry. A new system-managed environment is defined from a base Docker image plus a conda specification. Current environment. Environment image creation fails. Build diagnostics show that the workspace cannot reach the private registry from the default image build path. The conda file also contains several unpinned dependencies. Business requirements. Restore reliable environment builds and preserve reproducibility. Technical requirements. Keep the registry private and use supported Azure Machine Learning image build behavior. Which 3 actions should the team take? Choose 3. Choose every option that satisfies the requirement. Choice A. Review the environment build log and build failure analysis to isolate registry and dependency errors. Choice B. Configure an Azure Machine Learning CPU compute cluster with network access to the private registry for image builds. Choice C. Pin important Python, pip, and conda dependency versions and register the corrected definition as a new environment version. Choice D. Enable anonymous public pull access on the private registry. Choice A. Modify the already validated environment version in place so historical jobs silently receive the new packages. Select option A. Review the environment build log and build failure analysis to isolate registry and dependency errors. Option B. Configure an Azure Machine Learning CPU compute cluster with network access to the private registry for image builds. And option C. Pin important Python, pip, and conda dependency versions and register the corrected definition as a new environment version. This is correct because environment build diagnostics identify the failing stage. When the workspace registry is private, supported image build compute can provide the required network path. Pinning dependencies improves reproducibility, and dependency changes should produce a new environment version. The incorrect choices fail for the following reasons. D. Public registry access violates the security requirement. B. Silently mutating a validated version breaks reproducibility and historical lineage. Exam tip. For environment failures, inspect build analysis. Fix private registry reachability with supported image build compute and version reproducible dependency changes. The next item is question number 154. Scenario. An Azure machine learning pipeline contains a deterministic pre-processing component. A later pipeline submission appears identical to a previous successful run, and the team wants Azure machine learning to reuse the prior component output rather than execute the component again. For each statement, select yes if the statement is true. Otherwise, select no. Review statement 1. The component definition should have is_deterministic set to true for its output to be eligible for reuse. Review statement 2. Force rerun set to true on the new pipeline favors reuse of unchanged component outputs. Review statement 3. Changes to component code, environment definition, inputs, parameters, output settings, or run settings can prevent reuse. Review statement 4. When reuse criteria are satisfied, Azure Machine Learning can reuse the previous component output instead of rerunning that component. For the first statement, choose yes. Deterministic components can be considered for output reuse. For the second statement, choose no. Force rerun forces child jobs to run and disables normal reuse. For the third statement, choose yes. These differences change the reuse identity of the component execution. For the fourth statement, choose yes. Reuse avoids unnecessary component execution and can reduce time and cost. Reuse requires deterministic, unchanged component execution with force rerun disabled. Proceed to question number 155. Take extra care here because this is a hard question. Consider this scenario. A real-time model uses features from an Azure Machine Learning Managed Feature Store. Training and online inference must use the same declared feature dependencies without manually duplicating feature names in scoring code. Arrange the 5 actions in the most defensible lifecycle order. Build the sequence from the following entries. Entry 1. Package the feature retrieval specification with the trained model artifact. Entry 2. Use the packaged feature retrieval specification during online inference to initialize feature lookup. Entry 3. Create the feature retrieval specification that declares the required feature sets and feature names. Entry 4. Register or materialize the required version feature sets in the Managed Feature Store as required by the solution. Entry 5. Use the feature retrieval specification to retrieve feature values when creating the training data. Arrange the items in this order. The first item is register or materialize the required version feature sets in the Managed Feature Store as required by the solution. The second item is create the feature retrieval specification that declares the required feature sets and feature names. The third item is use the feature retrieval specification to retrieve feature values when creating the training data. The fourth item is package the feature retrieval specification with the trained model artifact. The fifth item is use the packaged feature retrieval specification during online inference to initialize feature lookup. Here is the technical justification. Version feature sets establish the source features. The feature retrieval specification declares the model's exact feature dependencies, can drive training data retrieval, and can be packaged with a model so inference initializes lookup from the same declaration. Remember this distinction for the exam. A feature retrieval specification links training and inference to the same declared feature dependencies and can travel with the model artifact. You have completed set 4 of the AI-300 Microsoft Certified Machine Learning Operations Engineer Associate Practice Question Series. How did you score? Share your result in the comments. Work through all the sets to build broader exam readiness and cover more practice questions. Please like this video, subscribe to Tech with Koushik, and enable notifications for more certification exam preparation content. Thank you for watching, and I will see you in another practice set.